Chapter 10, XM, Extreme Manufacturing. My first trip to Seattle took place in late October 2018 as Halloween night approached. I had been to the United States many times before, but never to Seattle. That was going to be a special occasion. Joe Justice was moving to a new home, and that would be the last Scrum Master course inside the original Wikispeed lab. I had fantasized about that place for a long time. Having written the book Scrum for Hardware, I knew everything about how Joe Justice and Team Wikispeed had managed to make it to the X Prize Award. I had seen photos, heard stories, and seen videos, but in person, it was going to be a different story. In that place, extreme manufacturing appeared not only for the various signs hanging on the walls containing the method's principles, but that blend of brilliance, volunteerism, and discipline flowed from every corner and every shelf. Joe Justice had managed to embody the spirit of the Silicon Valley startups in his garage. Simultaneously, similarly to Wikipedia, gather a group of volunteers around an ideal, a new world in which ecologically sustainability could go hand in hand with sexy, super fast racing cars. Extreme manufacturing is not just an engineering practice. It is a way of thinking, a way to combine fun with innovation and productivity. It's no coincidence that companies like Boeing, John Deere, and even Tesla have become fascinated by it. And as of today, you probably will be too. I wish you good reading. Paolo Samichelli, author of Scrum for Hardware. Scrum Masters are trained in establishing a company and work management framework that allows for more rapid change at a lower cost than previous management methods. For example, in May 2020, Elon Musk, CEO of 5 companies, announced the company would move a factory employing 10,000 people from California to Texas or Nevada the following week. Ultimately, an alternative resolution was made. Let's correct that now. And the factory move was not necessary. Update, in the following year, Musk moved the entire headquarters because the political climate was too dramatic. The political institutions in the state of California, Elon said there was less drama in Texas. And so he moved the entire company headquarters in under a year. However, the question remains, could the company have done it? In this case, move the manufacturing facility of 10,000 people. And what other company in the entire world of that size has a management structure and ability to execute that they could embrace change so large as to move an entire 5.3 million square foot factory producing 4 car models and energy products across state lines in 1 week and have any government officials and shareholders believe they could? This is agility, and Scrum Masters create the Meta Scrum meeting where decisions of this magnitude can be discussed as often as needed and distributed to all team backlogs for action within 15 minutes. This is why I have a problem when I see established management firms publishing books on agile leadership, and they talk about decision-making cycles of a year or a quarter. Oh, it's got to be able to be called on demand anytime and not be disruptive. So the rhythm of decision-making needs to be less than a day. In a company like Tesla, it's around every 3 hours. So if your agile leadership initiative is saying, and then the traditional management has their budgeting cycle for the year or 9 years, that's not what I'm talking about here. So let's see an engagement for extreme manufacturing that can result in daily change or faster, like 3-hour cycles. With this framework in place, the next question is, what do we do with an organization's newfound superpower of ultra fast and ultra cheap change? This is a product owner prioritization question, and we ask you to refer to our seminar and book Product Owner, www.abi-agile.com/en/book. The following question is, how do we do the work? This is the realm of engineering practices and technical practices, which does deserve a book on its own. However, we will provide a set of them right here. To go deeper on agile practices for hardware organizations, we recommend the second half of the book, Scrum for Hardware by Paolo Samichelli. The first half of the book is the story of Paulo and Joe Justice's life. Let's edit that. If you are not an enthusiast of the history, Joe Justice recommends you skim or skip the first half of the book and dive into the deep technical practices Paulo explains very well from there forward. In this chapter, we will provide rapid, tactical advice for Scrum Masters who now have an agile organization, but engineering teams not yet comfortable with, or possibly not yet knowing how, to design, analyze, build, test, and deploy in less than 1 month sprint, much less twice a day or more, like some of the faster agile hardware companies today. XM, or extreme manufacturing, is the set of technical and engineering practices to design, analyze, build, test, and deploy hardware in 1 week or less. Starting in 2006, Joe Justice observed what was required once his automotive manufacturing company, Wikispeed, was able to design, analyze, build, test, and deploy road legal cars and race cars within 1 week. For more on Wikispeed, we recommend Joe Justice's book, Wikispeed, Ultra Fast, Ultra Efficient, Ultra Fun. The XM practices are playful, fun, and absolutely necessary for a sustained sub-week hardware sprint. These have been used in Lockheed Martin Space Systems, Toyota, Airbus, Ariane Group, Bosch, Daimler, Mercedes-Benz, and more globally. Joe Justice would like to thank Peter Stevens for inviting Joe to teach the first seminar on XM in May 2013, and then publishing the XM practices in 2013, then publishing the handbook of the practices in 2020, titled Extreme Manufacturing. XM is currently defined as 7 practices and 11 principles. The practices are intentionally playful and embody Joe's observed philosophy that morale multiplies velocity. The goal here is to help create the brain chemical mix that is highly creative, yet highly competent with speed, required for engineering and building simultaneously, among other skills, for 1 week complete hardware sprints, culminating in tested releases. As XM practices. 1, always open. We find inspiration, the real driving, passionate, jump out of bed inspiration, comes at unpredictable times of day or night. We find value in reducing friction, frustration, and delay between the moment of inspiration and the serotonin and oxytocin release of doing. We also find value in reducing time to the mental stimulation of learning, if the inspiration resulted in an improvement or a move backward in capability. So when you're inspired, we want a feedback loop as fast as possible to know if we were successful or if we learned something through a mistake. If that feedback loop can be instant, that would be the ideal. It is top priority to keep the energy in the team at a sustainable near maximum. All Wikispeed shops are required to have keypads or combination locks where anyone credentialed to access the facilities can enter 24 hours a day and 365 days a year. This creates immediate awareness that all team members are trusted, empowered, and quite literally have the keys to the kingdom. This practice is recommended, and Joe Justice will say success likelihood is reduced without it in all agile hardware products. It is the first practice of XM. 2, snack shelf. As irrelevant as it may sound, nearly all Silicon Valley companies offer unlimited and round-the-clock barista or barista poured espresso drinks, coffee, tea, healthy snacks, and alcohol. There are many reasons for this, and maintaining energy and feeling safe, cared for, and nurtured explain the root of most of these reasons. Stocking unhealthy snacks does lead to the most present employees having lower energy over time and eventually increased health risks. Therefore, making the extra effort and sometimes extra financial commitment to stock healthy snacks amplifies velocity over time. Related, low blood sugar results in similar or even worse impairment than full drunkenness, and in some states can put a human body into shock. Reducing clumsiness is an important safety step, in addition to the morale boost a healthy snack can sometimes provide. Hosting alcoholic drinks varies from culture to culture. However, it has been observed that organizations that do stock alcoholic drinks for the teams, whether the teams drink them or not, have a much higher pace of innovation fruitful experimentation, self-reliance, and self-management. Joe Justice has said, the more the work area feels like a wild party, the higher the sustained velocity over time. Elon Musk seems to think similarly, with a tiki bar at the top of the SpaceX launch tower in Texas and a rave cave in Gigafactory Berlin. 3, safety shelf. Almost as important as the snack shelf. The safety shelf visibly holds all the minimum required safety gear to complete the work in the sprint's backlog with safety. This is typically face shields, dust masks, hearing protection, protective gloves, possibly hard hats, sometimes welding aprons and gloves and welding eye shields, and always a very well-stocked first aid and first response kit. The most frequently used items here are Band-Aids for minor scratches or splinters. Wikispeed, for example, in operation since 2006, has not yet needed to use more than a Band-Aid. This shelf also typically has a large front font printed paper taped to it, giving the address of the facility we are in now and the phone number for emergency responders, so that even in a panicked state, a team member could contact emergency response and give clear and concise directions to their location. The safety shelf, practice 3, was originally practice 2, until Joe Justice worked in more and more large organizations incapable of completing a project within a sprint. These clients waited hours or even days for separately trained facilities groups to get a 1 meter, approximately 3 foot step ladder, or to hang a whiteboard. In these organizations, they benefited from taking their own initiative and taking an acceptable level of risk, using the phrase safety third, without ever defining what came first or second. Safety wasn't last, but it was not the first priority over innovation and success. Instead, safety would be respected, but not used as an excuse for inaction. The success of this phrase has caused XM practices to be rewritten with the safety shelf as the third practice. 4, visible inventory. The physical layout goal for all XM operations is to have a point where a team member can stand, and without walking anywhere else, see every tool and inventory item needed to complete the current sprint's backlog and achieve the current sprint goal. Scrum Masters are supported by their teams with cards to complete early in each sprint's backlog to bring the facility layout and stock closer to this ideal. Some sprints it is not achievable. However, velocity increases and frustration reduces as we get closer to this ideal. 5, Kanban of tests. A group Scrum board is required. We want a big, actually, I think for branding purposes, more people are aware of and responding to group agile board. We want a big visible value stream map to the sprint goal, with the sprint backlog flowing across it, with all teams contributing to the sprint goal having their own row or swim lane, and velocity and quality measures are posted. We also need to phrase the work in terms of the test required for the work to meet the definition of done, and achieve the level of quality required to be truly complete for our sprint goal. Without phrasing the work as a test, developers often overbuild or underbuild, or build additional features that may be needed, but in actuality, seldom or never used. That may be perceived as needed, but in actuality are seldom or never used. Test-driven development focuses the team and creates the goal of lean, using less stuff without frustrating the customer. This succinct definition of lean was provided by Tom Poppendick. Thank you so much for your clear thinking, Tom. 6, cleaning shelf. Fast-moving hardware teams create dust, metal shavings, carbon fiber edges on clippings, and other debris. If the debris is not immediately cleaned, work slows down. Team members are less likely to lay down on their back to understand a part from a different angle if there are aluminum shavings on the ground. Materials, delivery carts, and wheeled machinery roll over dust piles and sometimes veer off course enough to bump another machine in process and create a defect. A slowness grows around the work. We require a shelf with minimum equipment and supplies to maintain the workroom to the level we could safely walk barefoot and eat on the floor. This is part of the 5S and 7S acronyms exported globally to great success from the Toyota production system, And the reason it deserves a place in XM is the speed enabler. A clean shop does look good too. Part of the release definition of done before the sprint goal can be claimed as complete is that the facility must be at least as clean as it was at the beginning of the sprint. Hardware sprints of 1 week are the norm in Joe Justice's Team Wikispeed, and some hardware sprints of large, complex, regulated, and certified physical products and projects with embedded software have been recorded as quick as 27 minutes. This requires a high level of technical excellence, technical practice, automation, and cross-functional teaming to reduce wait states, and a pristine, clean facility. 7, skills posters. All machines and some materials are positioned under posters or have posters attached directly to them. These posters, printed by a standard office printer, provide the essential steps to complete the work safely, quickly, and to the required definition of done or quality bar. These posters are only 1 page, have large fonts, and prefer graphics. They are not a complete training on a machine or material. They are a reminder or an introduction. In combination with pairing or swarming or mobbing with 1 or more experienced team members, these posters allow someone new to the work to complete the work. An elementary example from Team Wikispeed, where many team members arrive each week who have never used a wrench before, is below to illustrate the point. Bolting. Bolt diameter is listed, bolt length, a bolt thread, bolt grade, the strength grade, taper, torque specification. So this is your definition of ready, definition of done, and essential necessary vocabulary to speak intelligently about engineering with this bolt. From this, you can back calculate the available workload, etc. And it's on 1 page, 1 font size. I will read it. Bolting. 1, bolt diameter, 3/8. That's of an inch. Sorry about the imperial measurement. We standardize on 3/8 inch diameter bolts. Any part we make uses bolts of this diameter, meaning we standardize on 9/16 ratchets and wrenches, which is the size of the head on a standard 3/8 diameter bolt. This also means we standardize on 3/8 drill bits. This simplifies our most used inventory. Since parts we buy may have any type of bolt, we do need a full range of tools, but only multiples of tools of 3/8 bolts. 2, bolt length, shortest that fits with 2 washers and a nylon lock nut. We use the shortest bolt that will fit each part, allowing for a washer on both ends and a nylon insert locking nut. Nylon insert locking nuts can be reused in prototyping. The nylon doesn't wear out if tightened multiple times, but is not a throwaway part like some other locking nut types, and have excellent resistance to vibrating loose. 3, bolt thread, 24 thread pitch. We standardize on 24 thread pitch bolts. That makes the entire measurement 3/8 by 24 by the length of the bolt, grade 8. This is considered fine thread, or many threads per inch, for a bolt of this diameter. The more threads, the more strength the bolt has to hold the nut on. Conversely, coarse threads hold softer materials like wood and aluminum, as there is more material gripped between each thread. Since we are gripping into grade 5 or higher nuts, fine threads will give us much more gripping strength. 4, bolt grade 8. We standardize on grade 8 bolts. This is visible on the pattern and printed on the bolt head. This means each bolt can hold the entire weight of the Wikispeed car, ×4, with a safety margin to spare. 5, taper. That's the, does the bolt, is it straight or does it funnel in? None. Our bolts have no taper. However, brake line and fuel line connections do. This means the diameter at the end of the bolt is larger than the other end. These tapers are standardized, with names like NPT or AN. The most reliable method to measure them is to use an AN, then NPT thread gauge to see which fits better. These are hard to find. Most specialty stores do not even stock them. Without these tools, the next best method is gently hand tightening a corresponding fastener on and label the size that slides on smoothly. For this reason, we avoid taper and attempt to clearly label in marker the required taper and size on any part that we do buy that has taper, such as our brake master cylinder and fuel tank. 6, torque specification, 25 foot-pounds. Again, my apologies for imperial measurement. These should all be metric for global standardization. All of our 3/8 by 24 by N grade 8 bolts are tightened to 25 foot-pounds. This can be checked with a torque wrench set to 25 foot-pounds. It can be approximated for prototyping by pressing down on a ratchet or wrench with approximately 1 foot long handle with approximately 25 pounds of force or weight. Iteration, add a graphic of a bolt with a washer on each side of the part and a nylon lock nut. Iteration, put URL to video of each of these here. You can see the iterations are even labeled saying, if you have time, please add these to the sheet. And so anyone is empowered to update the sheet. XM principles. The 11 XM principles apply broadly to many, possibly all types of hardware agility. The goal is to establish thinking patterns which create self-organization and complex adaptive systems in hardware teams that produce product in short sprints. These principles also were recorded by observation in Team Wikispeed beginning in 2006 and being refined as part of the Scrum Hardware Guide by Joe Justice et al. In 2017. 1, optimize for change. The first principle is that by optimizing to make change affordable and fast and less frustrating, even late in development, we will reduce cost more than optimizing for cost over speed. If a supplier is across the street, who can deliver in 5 days or less, but cost twice as much as a supplier with an 18-month lead time, XM organizations will choose the supplier across the street. The cost of the project, accounting for salaries, wait states, feedback loops, cost of delay, and lack of enthusiasm due to not being able to validate new ideas for improvements, adds up. It is cheaper to use the faster but more expensive supplier even before we have a crisis or a recall, where cost of response is increased. I don't need to use words like exacerbated. Many companies work on multiple projects at once to make use of the wait time from long lead suppliers. This adds even more cost of delay, as we see in Chapter 11, Focus. This principle is observed in every aspect of development. For example, Joe Justice was working with a missile team. They had previously defined modules. The missile was able to be disassembled by the trained team in 5 minutes. When team members tested new hardware and circuits multiple times a day, they could place those parts into the missile for integration testing multiple times a day. Over time, additional wires and cooling lines, frequently shielding shapes, and mounting brackets, frequency shielding shapes, so blocking interfering frequency. They're like little shields. Let's say shields. That's more clear. And mounting brackets were snaked across the interfaces. This slowed disassembly. Splitting the missile into its modules now took several hours. Worse than this, it was frustrating. Several wires had an optimized ultra lightweight connector that, once secure, was very reliable and compact, but was difficult to thread through a tiny bulkhead opening with a specialized tool. This introduced almost an hour of try and test and try again in order to reconnect the wire successfully. The team became frustrated. The team became so frustrated, they stopped physically testing, and the pace of new tested development dropped, and the pace of development dropped, and the total project cost increased, and the price of the product increased, and sales reduced, and the contract came under scrutiny. The solution? Several sprints of introducing new upgrades and features while simplifying the interface, so the modules could be robustly plug and play disconnected and reconnected in less than 5 minutes without special tools. This added weight and size to the missile. The pace of rapid iterations resumed, and the missile was able to be reduced in size and weight back to its original specification and even better in 3 sprints while maintaining the interface. This isn't the importance of optimizing for change. changes in tooling, materials, personnel, even goal. 2, object-oriented modular architecture. An extra large project is really 18 extra small projects waiting for modular architecture. Joe Justice. Some projects are so large and so complex that machinery and methods do not yet exist to complete the product in a 1 week or less sprint. One sprint includes all of the following: design the product, CAD, analyze the product, automated computational fluid dynamics and finite element analysis scripts, build, CAM, computer-aided machining, machining operations, procurement, line operations, test, automated robotic testing and inspection, software testing through automated scripts, self-testing of small products using IoT, Internet of Things, unit testing, integration test, business value test, script-driven automated cost test, automated durability test, accelerated aging, and deployment, marketing photography, packaging, online user training and service training updates, shipping strategy, vendor strategy, reseller agreements, record demonstration videos for key personas such as salespeople and purchasing influencers. This is a problem with managing complexity. A solution here is to split the project into modules that may be developed in parallel. These modules are unit tested independently. The modules also share a standard known interface, agreed to and built as a test fixture before design starts. Each module can be tested and improved and deployed to work with the previous version of all other modules, completely independently of the rest of the modules in the system. A team or team of teams owning each of the modules allows parallel execution. The modules are split into sub-modules until the team or team of teams can produce the sub-module or module within a 1 week sprint. If all pieces of the product continue to be split until this size is reached and work in parallel with stable interfaces, the entire product or of any needed area, or any needed area, but that's really confusing here without introducing it. What I mean here is in manufacturing, you can also tape off a zone of an existing factory, and that area can now produce its result in less than a week. So you can do this without even product thinking. You can actually do this in any production setting by taping off an area and applying XM to the area. But I'm not sure how to explain that. This sentence is already super long. Anyone who might help me in editing, please on YouTube, put it in the comments or tweet to @JoeJustice and try to write this paragraph differently. You could even put a proposed different paragraph right in the comments on YouTube if you like, and I'll credit you as the contributing editor, or depending on the size, even a contributing author. Or any needed area is able to be improved within a 1 week sprint. As teams improve, this sprint length can be shortened, and ultimately releases are continuous throughout the sprint, with a sprint review of all releases at sprint end. Tesla, for example, releases 27 changes in hardware in production on the Model S luxury sedan per week. The rate of change on the Model 3 compact luxury sedan is not publicly shareable, but we can safely say it changes even faster. Other organizations have leadership saying the company must get agile or die. These companies still have multi-year release cycles. This means the company has not yet made the change to agility throughout much of the design and manufacturing organization. These are companies such as Volkswagen Group, including Porsche and Bentley, and Ford Group and Bosch. A fast-tracked minor model change in these companies is a 2 to 4 year cycle. For more examples on modularity, please refer to the book Wikispeed, Ultra Fast, Ultra Efficient, Ultra Fun by Joe Justice. 3, test-driven development. Creating the fastest, simplest, leanest solution to a given test is only possible if we start with the test to pass. The practice here is to first set up the robotic test or program the simulated test. For example, we would purchase the robotic testing device for a stress or strain test of part strength, or produce finite element analysis, FEA, simulation of a strength, stress, and strain test. Automated tests run continuously as new part ideas are drawn. The goal of these tests is to take the effort up front to make the tests run fast and with the least frustrating setup as possible. Ideally, the results of the test are traffic lights. Green shows we have improved over the last best design. Yellow shows we aren't any better than the last best design. Red, we are worse. Each color also indicates where the part needs improvement. This gradient color display also shares some quantification of how much better or worse the new idea is compared to the last best design. If these tests are rapid enough, we can adopt a test and learn approach to designing in hardware. David Snowden's Cynefin framework recommends a test and learn approach as the fastest way forward in complex work. As you may remember from chapter 5, where? An XM facility at sprint start is typically a row of robotic test machines waiting for a part to evaluate, with posters on each machine explaining, using new hire-friendly words, how to place the part, execute the test, and interpret the results as red, yellow, or green. For colorblind individuals, we adopt the Toyota convention that red is also drawn as an X or cross, yellow as a triangle, and green as an O or circle, in addition to being displayed in that color with a black outline. 4, contract first design. The contract, also called the interface, is the input and output, the I/O, of each module. The input and output are how things connect, what parts touch, and what heat or stress or electricity, including data, goes across each. We don't need to know each signal, for example, but we do need to know if data or power is required. Specifying a USB-C or Ethernet connection is often enough. The specific data transfer can be defined over time as the sensor and processing strategy develops. For stress and strain limits, we overbuild to allow more stress and strain in the future. While that adds material and design time now, it allows rapid iteration. Each iteration allows us to improve. Wikispeed observed weight and cost savings come each sprint. In XM, we recommend to save that weight and time elsewhere. The return on investment of an overbuilt interface tends to come within 3 sprints. In the end, an interface is able to be completely modeled by software and completely automated by software testing. This is because an interface, the I/O, is stress and strain to hold the parts together. Stress and strain are modeled by FEA, or finite element analysis, which is scriptable and automatable and able to be run in the cloud in minutes or even faster. The other part of I/O, electricity or fluid movement such as temperature, fluid transfer, air, and vibration, are modeled by CFD, or computational fluid dynamics. CFD is also scriptable and automatable. Engineers are able to develop a pattern library of interfaces and rapidly choose between them, possibly customizing if needed, in less than a day, and in some cases, minutes. For example, choosing USB 3 or USB-C, or choosing which bolt pattern a car tire will use can be fast decisions. These modular interfaces are then physically produced for testing. The interfaces are often an aluminum plate with bolt points drilled and electrical cable connections mounted. Electrical connections typically start by being wired to a laptop on one end to simulate input and output. Teams make these interfaces at the start of each sprint or check them out from a part library. The team then executes a backlog of what tests need to pass on the interface in the future sprints. An interface without the rest of the module is called a stub or mockup. Every sprint, the team not only builds product to pass the current sprint goal, but also updates or builds new tests and interfaces to prepare for the next or future sprints. This is part of the definition of ready, or what must be in place and tested before a sprint goal may be committed to in a given sprint. The definition of ready is developed and evolved during product backlog refinement, an activity discussed in Chapter 12, Plan. Note, interfaces may change at any time. provided the team on both sides of the interface agree. This discussion may be held at any time and typically occurs using the meta-scrum format. The agreement is often documented by taking a picture of a whiteboard diagram. This picture includes notes describing the new interface agreement and the necessary signatures. These signatures and a date stamp are from the product owners, who are ultimately accountable for the budget. We also include the signatures of any other relevant parties, such as safety leads, certification officials, and technical experts. The picture is then recorded to the project data store, which may be YouTube or a private encrypted team site, or Atlassian's Jira software, for example. 5, iterate the design. Elon Musk writes, if you have a high production rate, you have a high iteration rate. For pretty much any technology whatsoever, the progress is a function of how many iterations do you have and how much progress do you make between each iteration. If you have a high production rate, then you have many iterations. You can make progress from one to the next. Elon Musk, CEO, SpaceX. The speed of innovation is bottlenecked by the speed of iteration, as is cost of delay, as is enthusiasm of engaged team members, and much more. This is the most critical currency for our project. And in fact, this is the measure Joe Justice uses of an organization's agility. How long does it take to go from idea to done product or achieved goal? If it is 1 year or more, that is a long sprint, especially when SpaceX is currently building a new designed Starship rocket once per month. Actually, it's about every 1 week now. And the rocket engines for a SpaceX Starship, the Raptor engines and others, are made in 2 days, designed, built, test fired, and installed on a rocket in 2 days. So please read this section XM seriously to see how you can go that fast. New design Falcon rockets are launched once or more per week. Elon Musk is saying no two SpaceX manufactured rocket engines have been the same yet, as they continuously iterate the design to find improvements. To do this, all agile hardware teams must be guided by their scrum masters to redesign every sprint. The manufacturing organization, ideally with the product line starting in the scrum room where design is occurring, is on a cadence expecting a new design at the start of every production sprint. There is no separate production sprint. I'm saying sprint includes production. I should just say every sprint, because there's no separate production sprint. This way, change is not disruptive and morale eroding. It is expected, and the cadence can even become exciting and a source of inspiration and deep satisfaction. Iterating the design can be safe and affordable when using RedGreen Refactor. The RedGreen Refactor method is enabled by TDD, Test-Driven Development, discussed about in XM Principle 3, TDD. RedGreen Refactor here means first build a test, TDD, that does not yet have a solution. As the test does not yet have a solution, it is failing, returning a red light and an X for the colorblind. We then build the leanest, cheapest, fastest, possibly silliest thing that could possibly pass the test, which will in turn turn the light green and an O or 0 for the colorblind, well, a circle for the colorblind. We then refactor, dismantling our current solution to improve it towards the definition of done. This will temporarily turn the light red again as we work, as the test will now fail. When the test once again passes and the status light turns green again, we should have a solution that meets the test, but is also closer to the definition of done, which specifies our quality bar. In this way, we have RedGreen Refactor in a repeating cycle until we meet the definition of done. We can then create a more valuable test. The new test may be more strict or test another aspect of the value the product should provide. We then begin RedGreen Refactor again. The test here is typically a test of value that exercises an entire module. In the case of a Wikispeed car, a test would be a lap time on a specific raceway. In the beginning, the test is red. We had no car that could complete a lap on the raceway. When we first had something that could complete a raceway lap and had some semblance of a car, we turned the test green and celebrated. Then we took the prototype vehicle apart to refactor. We redesigned and rebuilt the vehicle in order to be more durable and more safe. And we repeated to reduce cost, make maintenance and use easier, make transporting the prototype vehicle to the track more easy, and eventually to improve the lap time itself, and so on. This process has never ended, provided the value of passing the next step is worth the estimate of effort and complexity to do so. Effort and complexity to complete the work includes the team's financial consumption rate, also called burn rate. Burn rate is the sum of salary and procurement and all expenses to operate the team for a sprint. We can estimate total project cost by multiplying burn rate by the number of sprints the developer's estimation predicts. For more agile financial management and value trade-offs, we invite you to attend our seminar and read our book, Product Owner. 6, agile hardware design patterns. Reuse and inheritance allow us to borrow from a tested library of hardware designs and parts. This library is inventoried to be by use and attributes to be reused, and these can be extended to produce new capabilities. An example is reusing the same cooling system by opening the cooling module assembly in CAD, verifying packaging can fit, checking the I/O to verify it can be adapted to match, and then engineering only the interface. Note, capabilities must match too. The reused module will perform the desired function and the desired capacity if the capabilities and interface match. This is because the interface includes both the input and the output. For example, X volume of heat is able to be output at Y frequency and returned N degrees Celsius cooler. The interface, therefore, creates a library of performance capabilities. But let us say the performance was not enough. Then we can inherit the design, modify it in as few ways as possible to exceed our new performance threshold. We then save the design and observe the automated regression test suite give us simulated capability, cost, aging, fit, impact deformation, and performance testing. At least for me now, that doesn't read smoothly. I'm going to come back to that. Inheritance can be even more powerful than reuse. If cost of the inherited product is similar and the interface stays the same, more often we retire the previous part number and replace all with the inherited assembly. This and many more time and cost-saving methods have been developed since the 1980s in the modern discipline of design patterns. The adapter pattern is to design and construct the simplest, smallest, removable, and hot swappable part as possible. To adapt one interface to another. The adapter pattern allows the module library to be produced in an abstract, idealized state and have the interface customized to match the current need. This greatly accelerates design by reducing the number of new parts to be developed and tested and maintained. Abstract factory. The abstract factory pattern is to tool our production line to produce a generic module. At the moment of production, one or very few steps in the line dynamically change to create the fewest changes possible to achieve a wide variety of purpose-built or highly optimized variants. The majority of the factory is abstract from any specific implementation, optimized to produce the generic parts of the assembly, allowing enhancements to be immediately available across all specific variants and reducing the support envelope. An abstract factory is typically has a decorator pattern factory to complete parts for use and sale. Support envelope. Support envelope is the number of supported variations or SKUs. Not sure I like that either. Might have to edit that more. The decorator pattern is a factory which takes in abstract base parts from an abstract factory and outputs completed parts. Often a wide range of completed parts are available from a menu. To visualize this, imagine a plain sponge cake. So actually a cake you would eat with no icing or decoration. This abstract cake is delivered into the decorator pattern factory, which we can imagine is a robotic icing machine that might look similar to a UFO catcher, a grab catcher, a toy grabbing arcade game. The person ordering the final cake may choose different flavors of icings and decorations and designs from an app menu, or even create a new decoration set. The final decorated cake is then delivered to the happy end user. Now imagine another abstract factory that takes in nearly complete cars, which we will call abstract cars. Each car are tested automatically and tagged with their performance level. So for example, Tesla tests the total power output of every Model 3 that's made. Some cars sustainably over time, while efficiently dissipating heat and operating with efficient use of electricity, can develop more power than others. So those are then tagged with metadata. How much power can this car fully warrantably generate? But by the way, all cars made, including internal combustion engines, have a variance in their performance capabilities. That's what Honda did to make their Type R cars. They would test every car and determine which had the highest performance, or at least which engines had the highest performance, and those would be labeled as Type R and then reworked to even further increase their efficiency. Well, Tesla does something similar with the Model 3. A customer purchases a car through an app and chooses the performance trim level with white interior and crimson red exterior. Cars are delivered until this customer order is at the top of the backlog. One of the highest tested performance abstract cars from the crimson red row is selected by robots. Red brake calipers with higher rated sustained braking force and superior cooling are selected and installed robotically. Performance software is downloaded and verified on the car. The white interior set is robotically installed. Each car exiting the decorator pattern factory then tests itself through all road legalization tests and drives itself onto a transport vehicle. The car is delivered later that day to the purchasing customer. So that's real. That's actually how the system works with that level of automation. That's the decorator pattern. The abstract car wasn't yet a performance Model 3 or any of the other Model 3s. And at delivery time, the car is customized with the fewest possible, easy to verify, lowest risk, repeatable steps to be the version the customer ordered. In this case, a performance Model 3, crimson red exterior, white interior. The wrapper pattern is a particular use of the adapter pattern. A specific part, for example, a part purchased from a vendor, has a specific non-generic interface. A bad solution would be to engineer our contract to mate to the in-house designed modules directly to the vendor part. If the vendor changes their interface, then we have to retool, and we don't know when that would be. That could shut our whole line down. So a bad choice would be to match their interface directly with our production, with our value add. We manufacture a wrapper in between, adapting the vended part to an interface we own or an open standard. This means if we switch suppliers, or if the supplier changes their design, we only have to change our wrapper to use the alternate part design. This is a risk mitigation step, and again, fits perfectly with our primary goal, principle 1, reduce the cost to make change, as opposed to a common sub-optimized goal in industries, reduced cost at the expense of agility. The facade pattern or facade pattern takes a complex interface and creates an elegant, simpler to think about and design with interface. For example, we could have 512 very small wires, carefully welded, each sharing a specific signal. Or we could terminate those into a chip and digitally communicate the information over Ethernet or USB-C, a simple supported standard as a facade. The Singleton pattern states if we use something often, it is best to have just one of it. For example, in automotive electronics, a modern automobile has more than 100 separate wire connections to chassis ground, or chassis ground, depending on the pronunciation you prefer, to the metal body of the vehicle for the only purpose of returning negative electrons to the car's battery. If any one of these chassis ground connections becomes loose, breaks, or has water or fluid collect nearby, the results could look like faulty software, a bad sensor, computational hardware fail, or others. To check every ground wire, the weather coating on the bottom of the entire interior would need to be removed. This is why many of us would simply sell our car if the check engine light comes on, but only on hot mornings after heavy rain. A solution to this is the Singleton pattern. Chassis ground is used often, so put it in just one place. A grounding bus bar is used instead of many individual wires. The ground wires increase in length to return all the way to the battery terminal negative ground bus bar. This lets us test for electrical continuity in just 2 places per wire, the grounding bus bar and the originating source. We also reduce waste in design. It is common for large projects to have multiple designs of varying quality to solve the same problem in different areas of the product. Enforcing the Singleton pattern means the best of those designs is checked into a reusable module design library and reused. The solution in the module library are then optimized in production in the abstract factory and used with adapters in across the entire product portfolio. There's a few edits that are needed here, I think. The solutions in the module library are then optimized in production in an abstract factory and used with adapters across the entire product portfolio. Okay, yeah, maybe that's okay now. An excellent example of this is the Tesla heat pump, first developed for the Model Y compact SUV and then adapted to previous and future products. Note, there are many more hardware design patterns. Please see our book, WikiSpeed, Ultra Fast, Ultra Efficient, Ultra Fun. 7, continuous integration development. When projects are large enough that it is not possible to complete the entire large hardware project or version of it in a single sprint, we recommend splitting the product into parallel executable extra small projects. We have now introduced a significant risk, integration risk. Integration risk is the likelihood that the various modules will not fit together and work together when reconnected. This is the top project risk in technical projects. Integration risk can cause the project to go over budget or over time or both. To reduce this risk, module teams use test-driven development, starting with the test, and are required to integrate with the test interface or stub or mockup every sprint before claiming any work is done. Continuous integration development means teams test their work against their known stable interface every day. At the group Scrum Sprint Review, any teams that share an interface are required to show that their parts successfully pass all automated and manual integration tests, if there are any manual integration tests. In high volume manufacturing, this step is automated, typically with robotic arms and scripted software. In electronics, this is an automated set of probes pressed down on the circuit board to verify continuity and run a list of scripted software tests. The software tests verify the business value of the circuit board is provided. Note, in all of these cases, the test can be thought of as simply testing the I/O, or input and output. By intentionally thinking of only testing the I/O, the test seldom needs to change, even if the part improves over many iterations while maintaining a stable interface. 8, line setup. The goal is low cost to make change in time and capital, so that the pace of tested and released innovation increases. With that in mind, several structural changes to the line become valuable. First, design becomes the first station of the production line. Whether the product design is virtual and downloaded via CAD and updated machine code for the line robots, or whether design is in person and on site, part of the value is that change is always accepted at the head of the line and expected. If the design team is not virtual and physically located on the production line, the ability to inspect the current manufacturing process significantly improves the rate of design innovation and optimization for manufacturing. This feedback loop between design and manufacturing is just as effective at increasing velocity and quality as the speed of the feedback loop between design and test. For this reason, the automated tests are also part of the same line and are visible to the design team. Mobile line lean production cells. Putting the line machinery on lockable casters is often recommended against by equipment manufacturers who want to reduce their liability. Most production machinery functions very well on lockable casters, even when producing significant vibration. The result of increasing machine mobility is a dramatic cost reduction. Cost is reduced to change the order of operation. Oh, that is correct. Cost is reduced to change the order of operations, switch one machine for another. Cost is reduced to program a machine on a test line and swap it in for a similar machine with a different setup and swap back as needed. Many agile methods of prototype line development and production line Kaizen are only possible if it is first cheap to change the line. Scrum teams as lean cells. Even more flexibility is Joe Justice's preferred strategy. Scrum teams as lean cells. Scrum teams mark their work area, typically as a large rectangle with brightly colored tape on the manufacturing center floor. Sometimes it's actually a hexagon or an octagon. It's not always a rectangle, but a shape, a geometric shape usually. The team prints standard printing paper sized signs on one side with their input requirements phrased as a definition of ready. If aluminum tube of these dimensions and with this surface finish and this alloy and this level of cleanliness arrive in this orientation in this quantity, our input is ready. On another side, their marked floor work area is posted definition of done, clearly stating their output. Posted on another side is the team's Scrum board, allowing the team through their Scrum Master to see in near real time their value stream map and where the work is queuing up. This Scrum board shows the team their internal team design, analyze, build, test, deploy process. It's actually their value stream map. This approach enables the fastest Kaizen or continuous improvement and most anti-fragility if each team has an empowered product owner and each team owns an entire testable module. Non-linear lean cells. The most flexible configuration is Scrum teams as lean cells, as described above, and non-linear flow of parts in and out of teams. Runners with carts or automated carts shuttle materials to meet each team's DOR or definition of ready and each team's DOD or definition of done. The advantage here is the direction and flow of the carts can change in real time based on which teams are producing what at what time. This is what Tesla currently employs at the time of this book writing, allowing 27 changes in production to the Model S luxury sedan in a week without disrupting the flow of the line. When new product introduction events often take months or years on most assembly lines, and non-linear lean cells absorb new product introductions continuously, while still achieving their highest rating ever given by Consumer Reports at the time, it is clear there is an available evolution of factory floor practices. Okay, that could be read much better. Tesla uses a non-linear line and has achieved the highest rating ever given by Consumer Reports at the time. So it's compatible with high quality is what I'm trying to say here, and I need to rephrase that. Something even more interesting to a Scrum Master is happening here as well. Linear production, when done well, is called single one-piece continuous flow. The idea here is no part of the production line is faster than the slowest part. The goal of single one-piece continuous flow is to achieve evenness and avoid separate stockpiles for rework or defects. This method was so much more effective at building quality in than previous craftspeople working on stockpiles that is still the goal of most production operations worldwide and the pride of the Toyota production system. But if we make an analogy between a hardware production line and a computer processor, single one-piece continuous flow is a single-threaded processing application, the slowest type. In single-threaded processing, one instruction is processed at a time in sequence. It is an ancient 286 processor as the prized goal state of most modern manufacturing. The Scrum Master, a trained expert in maximizing flow in the most modern sense, sees the opportunity to structure the manufacturing floor more like a modern processor. It is the cloud with N cores of compute able to be throttled on and throttled down as needed. These cores, capable of handling many different types of instructions, or in our manufacturing case, many different types of parts, are Scrum Teams as lean cells with nonlinear flow. They're also virtual. They can be partners or vendors if they're fast enough to meet the DOR and DoD. And that's a true dynamic organization where you can turn on and turn off individual cells and throttle those to vendors in 15 minutes or less, which I have done. This whole thing needs to be much more smooth. Probably this entire chapter needs a rewrite. For smoothness, it needs a read. These cores, capable of handling many different types of instructions, or in our manufacturing case, many different types of parts, are Scrum Teams as lean cells with nonlinear flow. Through cards in the backlog, teams know what is highest value to produce this sprint. And through modularity with known stable interfaces, TDD, DOR, DoD, quality is able to be preserved with speed while pivoting rapidly. This is the goal state as understood currently in the discipline of XM. When Team Wikispeed set this up, they designed and built a new car in 27 minutes, setting 4 world records in the process. All the practices above combined to make this possible with high speed, high quality, high morale, and mass volume. That car that was made in 27 minutes, there's a picture of it, designed, parts of it included new design. There's a picture of it in chapter 3, build. 9, continuous deployment. The last step on the line is the value the company wants to receive. Financial transactions, photographs of the customer receiving the good if appropriate, marketing updates, product photography, updated maintenance videos, and reseller agreements are treated as if they were physical steps on the line. All of these actions are processed as cards in the backlog of the Scrum Teams along the lines. In this way, a cadence of change ripples through the entire value stream of the product. All work is gated by the definition of done. This flow is visible to all teams on the group Scrum board. The group Scrum board represents the entire integrated product or business composed of the modules and goals owned by each team. 10, scaling patterns. As we think of the factory floor now as also the design center, test center, delivery center, and value innovation center, we see that adding additional lean cells or turning them off or repurposing them through Metascrum allows us to dynamically throttle production up and down, pace of innovation up and down, etc., without a typical change management initiative. Teams self-train just in time when they receive their new sprint goals. In Tesla, training is done through apps on your phone provided by Tesla, and they're basically YouTube videos, private YouTube videos. Some of them are public. Teams then self-organize into groups around shared interfaces and reform those groups when the teams with whom they share the interface change. This makes the organization anti-fragile. The business gains an anticipated, even exciting rhythm. This rhythm is never-ending continuous improvement and replanning. This is the healthy state of a complex adaptive system. Like a human body composed of billions of cells sharing I/O, our organization can be composed of billions of Scrum teams, each with their Scrum Master ensuring the known stable interface between teams. For more information on creating the organization structure for management, reporting, and functional execution, please see Justice's Law in Chapter 13, Sprint. For complete information on this, please see our book, Group Agile. 11, partner patterns. Most organizations create a detailed design and send it to partners for bid, agree on pricing, then sign agreements for the parts to be produced. Joe Justice consulted to a project with an 18-month wait caused by a supplier contract to provide a transmission. The transmission was for a prototype tractor. That transmission did not have tight size or packaging constraints, and none of the needed specifications were unusual for a tractor. The team had already invested many months and millions of dollars creating the detailed transmission design. In order to finish the tractor project that week, Joe called the vendor who had signed the contract to provide the transmission. With the newly trained Scrum team on speakerphone, Joe did not ask for the detailed specific transmission. Instead, Joe asked if there was any transmission in stock already made and able to be delivered today at the supplier that met the interface. In this case, no larger than a certain outer dimension, able to take X Newton meters of torque across Y RPM range and return Z Newton meters of torque across W RPM range. Yes, the supplier said, they had many transmissions that could meet that need in stock, and they were volume parts for which the supplier already had a functioning and tooled line, and they were a fraction of the price. The team bought the stock transmission and conducted physical testing of their completed tractor shortly after. The partner pattern here is to send the interface to the suppliers. And the next level of this pattern is to send test fixtures and test procedures directly to the suppliers. This empowers the suppliers to optimize in ways the design team, if separate from a supplier, could not know. This unlocks speed and cost and durability through supplier expertise, along with innovation through supplier expertise. That is not possible when detailed design is separate from manufacturing. If you designed it, you built it. When anyone designs something but does not build it, the feedback loop on the quality of the design is broken. Also manufacturability. This creates poor habits in design and sabotages the efficiency of the system and reduces the speed of innovation and confidence and satisfaction of all parties. This behavior is rooted in our biology as humans. The chemicals in the brain responsible for communicating to us that we are successful and rewarded are not released in the same level when we don't design, build, and test quickly and without being interrupted by other work in between. It is no wonder depression and antidepressant medications are at pandemic levels of use in countries with Sloan silos of specialists working only on part of a phase of work. The business process itself is robbing our teams of their endorphins, serotonin, and oxytocin, leaving us watching the clock, unengaged and racing to get home to consume something to trigger those chemical releases. The solution is not to abandon suppliers, but to treat them exactly like another Scrum team in the group Scrum. This means suppliers own a module with a known stable interface. That interface is then able to be executed in parallel with its own design, analysis, build, test, and deploy to a stated definition of done, and with a communicated definition of ready. The supplier does need to have the capability to deliver within a week if we wish a one-week sprint. Not all teams have to be on the same sprint cadence, but a sprint goal requiring an update from more than one module at once will not be able to be validated until the team with the longest sprint also reaches their definition of done, which can break the rhythm and cause arrhythmia. Expectation and growing through rhythmic stress and relax cycles causes strength building in humans. Arrhythmia lowers morale and lowers output across all teams affected. Arrhythmia even tempts the teams who are waiting to start another project, which would further slow down the organization as discussed in Chapter 11, Focus. Sprint 2 closing. In a 2-day course format, we would now be at the close of day 1. It would likely be 5 p.m. or 6 p.m., depending on if we started at 9 a.m. or 10 a.m. We would be about to bring wine and cheese on beautiful platters, beer and petite appetizers on engraved silver plates. We would be about to and encourage the attendees. Let's make that better. We'd be about to encourage the attendees to network with each other, exchange contact information. We, the instructors, would work the room to discover who may need additional services to purchase from our company, such as renting a certified chief agile officer to guide their executive agile transformation, or wanting to schedule Scrum Master courses in their facility to train their staff in bulk, or a leadership workshop to get their leadership team aligned on how to best support the organization and its Scrum Masters to maximize business value, or agile coaching to support teams underway. We would enjoy making friends and networking too. But before that, we would give everyone the homework. Our theory of organizational change is that if we want culture and process change, we actually need to change our mindset. If we want to change our mindset, we can use a deep collection of evidence-based science on how to change a mindset. Change in mindset physically is achieved. Let's learn from scientists on how change in mindset is physically achieved. What we are learning from neuroscience is that if we want a change in mindset, we actually have to build new synaptic pathways and myelinate them. We all build new synapses, even in extreme old age, contrary to some popular misinformation. While master meditators have been recorded building some new synapse connections while awake, the vast majority of new synapse connections are formed while we are asleep. To take advantage of this information, we want to expose ourselves to good, accurate, clear information on the new mindset we are considering just before falling asleep. To accomplish that, we provide a vetted article from Forbes for all attendees to read just before falling asleep. We let attendees know that we will ask some questions about the homework on the morning of day 2. The morning questions are not to ensure the homework is done or to check memory, but in order to trigger the newly made synapses. This triggering causes a myelin sheath or coating to form around the triggered synapses. Synapses with a myelin sheath fire more easily with less energy to trigger them and faster. This is physically what creates habits, which are the synaptic chains that execute quickly and trigger with low energy. If we have synaptic chains of an agile mindset, many types of thinking will naturally flow through the thought process of agility. A key habit we as instructors want our students to develop before day 2 is to be more interested in producing working product over following a plan. We will share the homework slide here. Before you sleep tonight, please go to leanpub.com, Scrum for Hardware. Select Read Free Sample. Read page 13 and 14. Thank you so much. Notice the Forbes article is embedded in Paolo Samichelli's book, Scrum for Hardware, and we provide the link to the free sample. This means we continue to have access to the article regardless of whether Forbes decides to continue promoting that specific article or not. Readers who want to read more before falling asleep can. We have led people to a more rich and more complete book than any single article. At this point, our Scrum Master course Sprint 2 burn down chart likely looks a lot like this. The seminar on the left was conducted in Japan from 10 a.m. to 6 p.m. across 2 days. The seminar on the right was conducted in Australia from 8:30 a.m. to 4:30 p.m. across 2 days.